Thank you. So this talk will also be about games where there is a graph structure and which somehow defines the interactions of the players, and we want to find sufficiently easy graph structures where it's tractable to find equilibria. But before we get there, I will start with a very general problem. This is the generalized Nash equilibrium. I didn't know about this, and it's known in many different names like abstract economy and pseudo game, and there are other names. So we have n players. Each player has a set of variables, and there is a utility function for each player. So this is like a usual game. The difference is that the set of feasible strategies of a player is a function of the strategies of the other player. So there is a feasible set which is a function of the strategies of the other players. I will show an example where this makes sense. Of course, you can argue that this way it's not a game because players cannot decide independently. And in a sense, this is true, but still it makes sense in some contexts. If you don't like it, you can also think of it as you can have utility minus infinity for certain outcomes. And you are only interested in Nash equilibria which has finite utility for every player. So solution is feasible for player I if given the strategies of the other players, the vector of player I is in this feasible set. And it's globally feasible if it's feasible for every player. And generalized Nash equilibrium is basically the usual definition of Nash equilibrium. So the solution should be globally feasible. And a player should not be able to change to another strategy to increase its utility. But now we are interested in strategy changes which stay in this feasible set of the player. So the difference from global constraints is that it's not that there is a global constraint which all strategies must satisfy, but these constraints depend on the player. How did this come up? So actually, this was defined by Debreu and Debreu for market equilibria, and they modeled the dependence of the budget constraints on prices. So one way that the theorem could be explained is that there are production players, there are consumption players, and there is a market player, and the market player sets the prices, and then the consumption players have budget constraints, but those budget constraints actually depend on the prices, which are set by the market player. So the feasible solutions of one player depend on the strategies of another player. And it's also good to model common resources, or what we will actually talk about is when some player has an obligation to provide a service for other players. And then the feasible strategies of this player depend on whether the other player actually requires this service or not. So, here is an example which maybe makes it easier to understand. So we have this service network game where players own certain arcs in the networks or certain shares in arcs. And it's a multi-commodity flow game, so each player has a set of commodities that that the player wants to route, and they can use their own arcs, or they can buy capacities at arcs of other players at fixed prices. And we say that a solution is feasible for the player I if she does not use the capacity that other players have bought from her. So this is a natural condition that in some sense the buyers are stronger. If someone decides to buy some capacity from you, then you cannot say that I don't sell it to you. You must sell that capacity, and you can only use the remaining capacity. So feasibility for player I actually fixes the capacity that I sells, but does not fix the capacity that I buys. So the player I can freely decide the amount of capacity that he buys, but not how much he sells, because that depends on the strategies of the other players. So most of the research about this generalized Nash equilibria in the optimization community, I think, is about how general can we get so that we still have equilibria. So what are the properties of this function and the utility function that still allow the existence of equilibria? But this talk, we go the other way. So we will look at a very special case, which is linear, where existence, at least under some conditions, follows simply from Kakutani's fixed point theorem. But we want a model where the interaction of players is restricted. It's restricted to providing services to each other at fixed prices, like in the network model that I mentioned. And the question that we want to answer is, how does the complexity of finding equilibria depend on the structure of these interactions? So here is the model that the special case, the linear special case that we consider. Yeah, it's a bit intimidating, but it's not so bad. So we have M services, we have M players and M services. Each service has a price. It's a unit price, so you can buy any proportion of the service and you have to pay proportionally. For player I, there is a set of services where he's a service provider and he has a share in this service, so he has to provide this proportion of the service ordered by all other players. And also, there is a set of services where player I is a customer, so you cannot order any service. It can be limited to some subset of services. And so each player has 3 types of variables. For each service, he has an amount of service that he sells. There is another variable for the amount of service that he buys. And there are some additional variables. And the strategies of a player are some bounded polyhedron in these variables. And there is a linear cost function on this polyhedron. So far there is, yeah? What is RIS? So it's a ratio that so this is the ratio that if you are a service provider of service S, then you have to satisfy this ratio of that service. So if the customers buy some amount of that service, then you have to provide RIS times that amount. Okay, I will formalize it in the next slide. So up until now, there is actually no interaction between the players. The polyhedra of the players feature different variables. The costs of the players are independent of each other. Sorry? Okay. Yeah, so this is the important point. So these are the ratios and variables related to the services. And so here is the interaction. The personal service equation of player I for service S is this linear equation. It means that the amount of service that player I sells is actually LIS times the total amount of the service bought by the other players. So this is the only point where there is an interaction between the players. There is no interaction in the utilities. There is only this interaction in the feasibility. And we say that a vector XYZ is feasible for player I if these are satisfied. And the utility of the player is, of course, the price of services sold minus the price services bought minus the cost. So the only interaction is in these equations and not in the utilities. So let's return to that service network example. This was actually introduced by Agarwal and Ergun, but not in this context, in a cooperative game context, but it can be formulated here too. So we have a directed graph with capacities, and each player has a multi-commodity flow. And now we let the set of services be the set of arcs of the digraph. Ri of E, for an arc E, is the share of the arc owned by player I. And we have the variable for the amount that I sells of that arc and the amount that I buys or uses. And there are some other variables for the multi-commodity flow problem. And so actually the only constraint where this variable, so the amount sold, appears in the polyhedron, so the polyhedron of player I is this inequality that you cannot sell more than your share of the capacity. And the personal service equation for player I on the arc is this, that the amount that you sell on that arc is your share times the total amount bought. And if you look at these, it actually works because if the solution is feasible for player I, then this is satisfied, and also this is satisfied. So it means that the total capacity used is at most the capacity of that edge. Note that this does not hold for player I if he is not a service provider on that edge. So if an edge does not belong to player I, then a solution can be feasible for player I even if the capacity is not satisfied on that arc. So this is a kind of strange concept that when we are looking at equilibria, then and say I am player I, then I can buy additional capacity even on arcs where which are so I don't have to satisfy the capacity constraints on the arcs which don't belong to me. I only have to satisfy capacity constraints on arc which belong to me. So it's a quite strong notion of equilibrium, because an equilibrium means that you cannot improve even by changing your strategy like that. Here's a simple example. So this is the graph. There are two players, red player and blue player. Red arcs are owned by the red player, blue arcs are owned by the blue player, and these are the costs, which now we assume that are the same as the prices. So, and red has one demand from U to W, and blue one demand from V to W. So the social optimum is clearly that red just uses this arc, and blue uses this arc, and you have a cost of 4. But now red is better off if he buys this arc from blue, and then he has a pass of cost 2. So the social optimum is not in equilibrium because red player has a better strategy which is feasible for him because he is not interested in satisfying the capacity in this arc. Now, if red buys this arc from blue, then blue actually must use this path, so VU, UW. So the equilibrium is that the red uses the UVW path and blue uses the VUW path. So you may ask, okay, there is an equilibrium here. Is it true that there always is an equilibrium in this situation? The answer is no. Yeah? The strategy of the flow here and how much and how much they sell and how much they buy. Yeah, but
the initial amount they have at the beginning is given. The R's are given.
yes, yeah, and prices are given. Yeah, and the point is that they must satisfy the property that the amount they sell is exactly what the others buy. That's the property that they have to satisfy.
But then that is not a strategy, it's fixed. Because given all everybody else's strategy, this value, this quantity is
Okay, but okay, this depends on how you look at it. So I didn't want to go into that, but actually you can be both a buyer and a seller on the same arc. So, but in this case, it's not interesting. That's why I didn't want to go into that. So it's easy to see that there is not always an equilibrium, because if you remove the VU arc here, then there will be no equilibrium. So the only solution is the socially optimal solution in the previous one, but we have seen that that's not an equilibrium. Yeah, you can also think, okay, maybe blue can preemptively buy this arc from red to prevent him from using it, but that's also not an equilibrium, because then for blue, that's not an optimal strategy. So there is no equilibrium in this instance. But there is a property which guarantees the existence of equilibria. It's that, I call it the safety property. So if we have a vector in the polyhedron P, not necessarily feasible, but in the direct product of the polyhedron of the players, then there should be, for every player I, there should be a vector in his polyhedron such that if he changes to this strategy, then the solution will become feasible at least for him. So each player can change the strategy to be feasible for him. It won't be a globally feasible solution, but feasible for that player. And then in this case, it follows easily from Kakutani's fixed point theorem that there is an equilibrium. And actually, a good thing about this is that equilibria will be the faces of some polyhedron, the polyhedron of globally feasible solutions. So no matter how many players you are, you always have a rational equilibria in this game. So now we can get to the, yeah? No, it's about, so P is the direct, so each player has a polyhedron. These are independent of each other, and P is simply the direct product of this polyhedron. And then, so if I return here, so we had this polyhedra, and P is just the direct product, and then we have these additional equations. So basically, the globally feasible solutions are this polyhedron intersecting with some linear subspace. Here I am. So, okay, so what is the complexity? In general, it's NP-complete to decide if there is an equilibrium. It follows easily from earlier results that, because it's proved by Kakutani that it's in PPAD. And what we proved is that it's actually PPAD-complete. So finding equilibria here is PPAD-complete. But the reduction uses a lot of services. So the question is, if there are few services, or the structure of services is simple, then can we find an equilibrium efficiently or not? And for this, we can define this interaction digraph, which I think this is the interesting point in this model, that it's not a graph now, but a digraph. So it's obtained by just adding arcs from each provider to each customer of each service. And we have a digraph because the customer influences the feasible strategies of the service provider, but not vice versa. The service provider cannot influence the strategy of of the customer. So it's a digraph, and what we could prove is that if the safety property holds, and every strong component of this digraph is a simple directed cycle, then we can compute an equilibrium in polynomial time. So it's only for simple directed cycles. And then this is the smallest open case. We have 2 players. We have 3 services, one offered by player 1 to player 2, and 2 services offered by player 2 to player 1. We don't know the complexity of this. So whether there is a polynomial time algorithm for this one, or there is or it is PPAD-complete, I have no idea. And there's a last slide. I quickly mention some additional results that it's a natural question. Actually, this is the question that Agarwal and Ergun were looking at. So how can we set the prices in a way that the social optimal solutions are equilibria? And the fact is that in the general model, we cannot. So it's even possible that we cannot set the prices in such a way that an equilibrium exists. But there are 2 special cases where it's possible. One is when, so this is a natural condition that you are either a customer or a provider of each service, but you cannot be both a customer and a provider. In that case, we can set prices like that. And the other case is when these service shares are optimal in the sense that we cannot change them to get a better social optimum. So somehow if the services are, so for a given service, the amount that the players have to provide of that service, or the ratio is optimal, then you can set the prices in such a way that social optimal solutions are equilibria. And in that case, even coalitions cannot get a better solution. So it's also stable for coalitions, not just individuals. And actually, this implies the results of Agarwal and Ergun, because in the multi-commodity flow game, it can be shown that it's this second case. And then we can set the prices optimally. So, thank you.